discussion on experimental exploration of granular motion on low-gravity planetary surfaces.
So I'm going to transition from talking about why we need simulants to simulate what we're trying to understand on these asteroids to why we need actual environments that are, can you go to the first slide, please? Sneak peek. Why we need environments that are also reproducing these asteroid environments, these low gravity environments. So this is a long title. It's experimental exploration of planetary surfaces, or how do we actually explore these planetary surfaces in environments that we have here on Earth? So my co-authors on this are Julie Brisset and Josh Caldwell, and a number of other people that I'll call out for a few of these different projects. So I'm going to talk about a couple of different projects we're working on, but first I'm going to give a little bit of motivation that is well known to everybody here, but it gives a chance to show more good pictures, right? So why do we need to do experiments to understand what we're looking at in observational data or where we're going to go to explore these surfaces? So our experiments we use to help with both scientific and exploration purposes. So these are just some pictures of different asteroids, Eros, Itokawa, different surfaces we've seen. And as we know, as Dr. Britt just talked about, we know that there is regolith on all of these surfaces. They're dusty, coated, airless bodies, anywhere from the moon to asteroids to other small bodies in the solar system. And so we can take observations, either with orbital measurements, things from here on Earth, and we can see what the surface properties are of these asteroids. But we haven't really, on very many surfaces, actually gone down to the surface to see what the regolith is like, how it's actually distributed on the surface. We have to infer all of these measurements from other observations. We can look at optical, spectral, thermal measurements, try to get at particle sizes, for instance, and maybe particle size distributions on surfaces. As Dr. Britt mentioned, we can use meteorites that have fallen to infer particle sizes and particle size distributions of these regolith properties. And you can also use cratering and different modeling efforts to look at how regolith is going to be distributed with depth on the surface of an asteroid or on the moon, for instance. But without sampling, it's difficult to actually see how these things are going to vary with depth, how the size distribution will vary. And so that's where experiments can come in. We can perform experiments to see how we expect these different properties to vary on different planetary bodies with different gravity than we see here on Earth. And we can also use experiments like this to help inform exploration activities. So one of the big things for SURVEY is that science informs exploration and exploration informs science. So we want to understand if we go to pick up a boulder off of an asteroid, or if we go to a dusty planetary surface, what are the surface properties going to be like when there are astronauts or rovers or landers interacting with that surface and sampling? And if you sample this top bit of the surface, as the OSIRIS-REx mission is planning to do, what is that going to tell you about things that are below the surface? If you know your size distribution of particles that you see right on the top, can you infer then what's happening beneath the surface farther down? So we can use a variety of experiments to try to understand some of these properties. So I'm going to talk about two experiments today that are new experiments that we're working on. SLOPE is the first one I'm going to talk about. SLOPE is an experiment that's looking at understanding avalanching and regolith movement in low gravity environments. So currently we are prototyping this experiment, and previous work has shown that avalanche behavior actually shows a dependence on the gravity level of the body that it's on. So we know we see mass movement on places like Eros, we see mass movement on the moon, the lunar surface, and previous studies have shown that there's actually dependence on what that slope behavior is going to do on the gravity level. So we'd like to be able to do experiments in which we can vary the gravity level and see how that affects the slope motion, how that affects the granular dynamics with different types of material properties and size distributions, for instance. So we want to use these variable gravity levels, and we can also look at things like seismic shaking, how that affects slope motion. So on an asteroid, if you also have a little bit of seismic motion, how is that going to affect your avalanching? And finally, we also want to look at a little bit of jetting effects. This is relevant to exploration. If you have a lander coming down that has jets to disturb the surface, how is that going to affect a sloped surface? It's also relevant to places like comets, where you have subsurface jetting that's going to disturb the surface. So we want to create some experiments that we can use to understand these properties. This is from a previous experiment showing how the sloping behavior changes with different gravity levels. So in this case, 1G is Earth's gravity. And we've done some preliminary testing just to start working on an algorithm to look at, if we have these slopes, how can we detect it with our video cameras? How are we going to look for these changes? So our first set of experiments for this is going to be done on a parabolic airplane. Parabolic flights are advantageous because you can set the gravity level of the flight. So they can go anywhere from micro G to like 0.1 G, so lunar gravity. So we can vary the gravity level of the environment that we're in, and we can see how that affects slope behavior. So we're going to do that again for just a box with a little bit of regolith in it. You can set it to different slopes. You can turn it and you'll have different slope angles, and you can see how that affects avalanche motion. And then we can also do things like induce vibration, have a little motor on there that vibrates the surface, and see how that changes our sloping behavior. And finally, we also will have a little way to do a little gas puff, a little injection that will disturb the surface additionally, so we can see how that changes the sloping behavior and this motion of regolith. And we can, again, do this for a variety of simulant types, a variety of size distributions. We're working with Dan Britt and DSI to use some of their simulants. We have lunar simulants, Mars simulants. There's a wide variety out there. And so the advantage of a parabolic flight is that you can get these variety of gravity environments in one set of flights. There's also other ways to vary your gravity. For instance, if you were on a suborbital rocket, you can send that up, you get microgravity environments, but you also get a range of gravity environments as you go from 1G through higher G levels at liftoff. Then you go in slowly into microgravity, and then you come out of it again. So you actually get a range of gravitational environments in those situations as well. So the next project I'm going to talk about is also using these microgravity environments, but it's actually using the microgravity environment of the International Space Station. So this is a project we worked on with some people at Johnson Space Center. Paul in the back, this is originally one of his ideas, I believe. And so the idea is that the International Space Station is a large object that's orbiting the Earth, but it actually has on board very low gravity. The gravity on the ISS mimics that of a small asteroid, or a relatively big asteroid, depending on the day, sort of. But so it has a low gravity environment that we can track. And so we can use the ISS to simulate what is happening on an asteroid. If you have regolith on an asteroid, what's going to happen when you have different shaking environments, or if you perturb the surface. So basically the idea is to use the ISS as an asteroid platform. So the way we did this is with an experiment called Strata. So Strata consists of 4 tubes. They're vacuum tubes, but not the way you might think of them if you've used vacuum tubes in your computers and TVs back in the day. So they're just tubes that have simulant. I'll show you a picture here in a minute, that are put into a rack on the ISS. And so these tubes have different properties, different compositions, but basically we use video data on board the ISS. Right now it's just a passive experiment to see what happens to regolith when it's in this microgravity environment. So I'll show you some pictures and talk about this a little bit more. So pre-launch, this is what our experiment looked like when it got packed to ship up to the ISS. And we have, like I mentioned in the previous slide, we have 4 tubes. There are 2 here that have glass beads. These are used for modeling purposes. So if you're doing numerical modeling, the easiest way to do that is with spherical particles, right? So we have these spherical glass beads in one of the tubes to really be able to match with our modeling and understand what's going on when we have these perturbations. So we have 1 tube with glass beads with 3 different particle sizes. So we can look at how this layering behavior changes. So we also have these are broken glass fragments that are about the same size distribution as the glass beads. And then we also have 2 tubes that have more realistic compositions. So 1 tube has a meteorite that we broke up. So a meteorite fell to the Earth. Dan found it and hit it with a hammer. Most of us hit it with a hammer. We had a fun party. So it came from space and we sent it back up. So we've sent bits of a meteorite back up into space. We have a specific size distribution, as you can see there, that we sent it up with. And then we also used some of the carbonaceous chondrite simulant that Dr. Britt was talking about. So basically, before it went up, it was in this nice layered configuration where you can see the distinct layering between the different particle sizes. That's great. There's this intrapulator down here. That's a trademarked name we came up with. It's a fancy word for scissor jack. And it compressed these simulants when they were in the tubes for launch so that it provides an overburden so that you don't expect as much motion that way as it's going up to the station. So ideally, these tubes would all be in their nice distinct layers when they get up to station. Then once it's up there, this intrapulator retracts and it gives space for the particles to move around. So it wasn't a lot of space. There's only about a centimeter or two for it to have motion, but that gives it gives this regolith space to move around when it's on orbit. And this is all that we have video data that's being recorded on board. So we have video of each tube, and I'll show you some of that here in a minute. And basically the idea is it's a passive experiment. We're just seeing what happens when we have these particles in this microgravity environment. We really don't know how the layering is affected by being in microgravity, and also with the vibration profile that we have on the space station. So it turns out that on the space station, it's this nice clean microgravity, very little, not very much of the time, because the astronauts are moving around, there's other experiments that are running, and so you actually get vibration profiles that change throughout the day. And that sort of can simulate what's happening on an asteroid, where you have seismic motion, maybe you have impacts that are creating vibration. So we're going to see how that changes the layering and the distribution of the regolith as this is on the space station. I'm timing myself, so. As this is on the space station for 6 months. So we actually just got data back today, I think, but we haven't seen it yet. But these are some initial videos from when we first got this data back from station. So this is the tube before it, or when it first got up to station. So you can see there's these red beads this is just the bead tube. Can you play the video? It's a little animated video. So you can see here, the intrapulator retracting, and it gives motion to these particles. Remember, we're in microgravity, and there's not necessarily a primary gravity vector on these particles. You wouldn't necessarily expect them to all fall, for instance, toward the intrapulator as it's opening. But there is this vibration and other things that are on the station that are causing the motion that we see here. So one of our challenges is to correlate those vibration and the motion that we see. So you can see here you have the red beads, we have the green beads and the blue beads moving around. So we're going to be tracking those, seeing how the layering is affected over time. I'm not actually sure of the time scale on that one. We take still images and we splice them together. On these next ones, I have the time scale. So this is a video loop about 11 frames, if you can play that too. And it's sort of hard to tell it's playing, except that you can see the bar moving on the bottom. So this is a relatively quiescent phase. This is 11 frames, and it was about 5 seconds between frames. So it's a short little period. But you don't actually see much motion. You can sort of see that there are some particles moving around here. This is a quiescent phase where you don't see things moving. This is the meteorite, or the simulant tube. So you can see we just have this we have a really compacted area. We have some chunky regolith. That's both big particles and clumps of smaller particles, we think. So we're going to look at how this evolves over time. And then sometimes you see a lot of action. So in the next slide, this is only 3 frames. There's longer chunks between frames, about 6 minutes between frames. But you see a lot of action, if you can play this one also. You see a lot of action with these particles moving around in this area. And you can see we have some fracture lines in the fines there. That's moving around too. So there's going to be a lot of data analysis for this and seeing how these things change over the months that we're up on station. And you can also see that we can see some of the other tubes. We have ancillary data of movement on those. Okay, so one of the things we can do with this is to look at the seismic data on station. So I just have some plots here. There are accelerometers up on space station. There's one mounted on our experiment. So we can correlate the acceleration profile with what we're seeing in the videos. So we're going to be doing that for both normal events and for off-nominal events. So this is sort of a typical profile. This is frequency and time here. And then this is just the magnitude of the acceleration that you're getting. So you can see certain frequencies are very strong at all times. And sometimes but this is a relatively quiescent period. There's no strong signal. Sometimes another experiment turns on, and you can see a really strong vibration profile from that experiment. So we're going to be tracking all of these things as we go. And so We also then, I'm going to wrap up here, we also then are going to get a lot of science data from this, and we're working on ways to expand this and really use this to understand some of our exploration objectives and our science objectives. So future experiments can be used varying the regolith composition, making active parts of the experiment to look at anchoring, for instance, in regolith, in microgravity. So we have a huge range of things we'd like to do, so we're working on that. And slope also could be on an ISS platform if you can vary the microgravity environment on there as well. So I'll wrap up with that and take any questions. Thanks. Maybe one question.
A quick question. Maybe you said it. I'm not sure the size of your tubes.
Mm-hmm.
What effect do edge effects have? That's a finite size as opposed
Yeah.
to like a much larger volume where you can isolate what's happening in the middle from the
Yeah, yeah. So our tubes are about 8 inches long and 2.5 inches wide. So we definitely know that we have edge effects due to not only being in a container, but also due to just interactions with the plastic walls. So that's one thing we're looking at, how that's affecting what we're observing. You can definitely see with like the red glass spheres that they are attracted to the walls and have interactions there. So we're looking at that and how we're going to pull that out in the data analysis, and then in the next phases, how we can mitigate that. Yeah, so it's just sitting there. And so we just take data throughout, takes images throughout the day at a certain cadence, and it's just going to be sitting there while it's up there. So it's going to last, I think, 6 months, maybe a year-ish, hopefully. So we're going to have lots of data back from that and lots of, hopefully, undergrads to look at the videos.